Okay,
so I have to thank and congratulate the organizers for their courage in inviting me here. Everybody else is talking about, I'm the person who needed to know how to pronounce Gerard. I didn't know until a few minutes ago. And so I don't have a story about having worked with Gerard. We sort of interacted in a rather extended Facebook discussion, which was the only time in my life I wrote as part of a philosophical discussion of one-act play, which, as I now know, was titled Waiting for Gerard. I have to hope that it'll turn out that Beckett actually meant his play to be Waiting for Godot, for the thing to work well now. But we had, and probably still have, rather strong disagreements. And my understanding is he asked me to be invited, which this is the one thing I can say. I've always found him very open to discussion and continuing discussion. And you can't ask for more than that, so thank you for that. So I do want to talk about Bell's theorem, because this is what it was all about. Some of this will actually reflect on some things that I disagreed about in the last talk. And a lot of it is it's basically exposition. There's nothing new by me in all of this, but and a lot of it I'm just going to be reading quotes, because the people who figured this out first said it often in a perfect way, and you just have to sit down and read them carefully. So let's start with Einstein, who began this whole thing. And there's this fairly famous quote when he's expressing the sense in which he believed that the progress of physics was leading to more and more locality. So again, let me just, and this is in a letter form. If one asks what, irrespective of quantum mechanics, is characteristic of the world of ideas of physics, one is first of all struck by the following. The concepts of physics relate to a real outside world. That is, ideas are established relating to things such as bodies, fields, etc., which claim real existence as independent of the perceiving subject. Ideas which, on the other hand, have been brought into as secure a relationship as possible with the sense state. All of this is very careful, I should say. When we read Einstein, he was always right on point. The same thing with Bell. So, all, you know, as secure as possible it's a term of art. He means it. It's the right thing to say. It is further characteristic of these physical objects that they are thought of as arranged in a space-time continuum. An essential aspect of this arrangement of things in physics is that they lay claim at a certain time to an existence independent of one another, provided that these objects are situated in different parts of space. That is, if I take two disconnected regions of space, or space-time, I should be able to characterize the physical situation here without reference to the physical situation there, and vice versa, and the physical situation in the union of those regions just follows from the physical situation in each of the regions. This principle has been carried to extremes in the field theory by localizing the elementary objects on which it is based and which exist independently of each other, as well as the elementary laws which have been postulated for it in the infinitely small four-dimensional elements of space. So in field theory, the fundamental physical ontology is localized in a way I was talking about, and also the laws themselves are localized because they're given by the appropriate kind of differential equations. So let me talk about both of these kinds of locality. There's an ontological locality and there's a dynamical locality, and they both come into Einstein's view, and he mentions them both in the passage. So, just terminology for those of you who are physicists. What we in philosophy use, and it scares physicists. It's scared, I mean, I don't know if Bell knew about it, but he reinvented this in terms of the term beables, but it's what we call the ontology of the theory, is just what the theory postulates to exist, to really be there. That's why Bell called it beables. So you have the elementary objects postulated by a physical theory, or the ontology of a theory. A local ontology is an ontology that can be globally specified in a space-time by specifying it in every chart of an atlas of space-time, no matter how small the charts are. So, you know, I have all of space-time. In a local ontology, I tell you what's going on in this little bit, in this little bit, in this little bit. They have to overlap, like the charts in an atlas have to overlap a little bit. But no matter how I break it up, if I specify all the little bits, then you give me all that information and I've specified the whole thing, right? So that's the locality of the ontology. There's a term of art in contemporary philosophy for those who are physicists. This is sometimes called the Humean mosaic. I won't go into a lot of detail about how that came about. That term is due to David Lewis. If a theory does not have a local ontology in this sense, then it's just not a local theory. Okay? And when you see that, you immediately notice that the wave function, and I'm going to, again, make a careful distinction of terminology here between the wave function and what I'll call the quantum state. Here I'm talking about the wave function, which it's a mathematical object, right? Any function is a mathematical object. That's what functions are. The wave function that we ascribe to a system, that we use to describe the system, because what we do in mathematical physics is we use mathematical objects to try to describe the physical world. The wave function is not local in this sense. And that's because of entanglement. Okay, go back. Sorry. Okay. That's because of entanglement. Why am I, all right, it's somehow not giving me the rest of that slide. Well, if I can't bring it up, I'll just read it. Why is that? Because, you know, if it's entangled, if I have a system of two pieces that are spatially distant and the two pieces are entangled with each other, and I want to ascribe a wave function or something like a wave function to each of the pieces, what I have to do is trace over the other part and use a density matrix. But the pair of density matrices that I get do not recover the full information of the original entangled state, right? If I have a singlet state of two particles, a singlet spin state, I can use a density matrix here and a density matrix here, each of which give me 50% probability for measuring the spin in any direction. But just knowing that tells me nothing about correlations between the two sides, right? They disappear. So I've lost information in going from the original singlet state, which will tell me about the correlations, to this pair of density matrices. So the wave function, the global wave function, if it's entangled, is not a local object. Now, that doesn't mean you have to give up on a local physics, you just have to give up on thinking that the wave function, this mathematical thing, is some kind of direct representative of some physical reality. And you can try and do that, but we'll talk about it. Oh, now I get it, okay. Okay, and so, right, if I specify the reduced density matrix for this room and for a slight superset of the complement of this room, again, I want these two regions to slightly overlap, like I do with the charts in an atlas. I don't get back the initial universal wave function because those reduced density matrices, that pair of reduced density matrices, will be compatible with different universal states. So that's due to entanglement, and then we have this wonderful statement that's already been mentioned, I think, in Yoss's talk, which is from the Schrodingers Cat paper, which is a wonderful paper. Again, I don't know, physicists, in my experience, don't tend to go back and read the original papers, but this is just a fantastic paper. So Schrodinger said, when two systems, of which we know the states by their respective representatives, enter into temporary physical interaction due to known forces between them, and when after a time of mutual influence the systems separate again, then they can no longer be described in the same way as before, namely by endowing each of them with a representative of its own. I would not call that one but rather the characteristic trait of quantum mechanics. And that's just a wonderful statement, right? Nothing to do with indeterminism, nothing to do with complementarity, right? It's entanglement that is the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. By the interaction of the two representatives, their psi functions have become entangled. That's when he introduces those dimensions. This is exactly where he introduces the term, as far as I know, for the first time in the literature. Now, let me give you this terminological distinction I like to respect between the wave function and the quantum state. The wave function is a mathematical item. And, as I said, the point of mathematical physics is to use mathematical items of one kind or another to represent the physical world. But not every well-defined mathematical object corresponds to anything physically real. So, a trivial example, take the center of mass in classical physics, take the center of mass of an object. Okay, that's a perfectly well-defined point in space. But there might be nothing physically there, right? The center of mass of a donut could be a vacuum. So you want to make a distinction between those parts, even mathematically, that can be even directly attributed mathematically to particular regions in space, those that are merely mathematical constructs, and those that are supposed to be representatives of actual physical items, which is what Bell called the local beables of the theory. And again, it's beables, it's an amazing thing, right? Ontology, fancy sounding term, I guess, but if you know your Greek, ta onta is just the beings, right? The things that exist. And logos, the account, right? So your ontology is your account of what exists. And Bell just rediscovered the term and anglicized it into beable, right? So from onta you get be. He was doing the same thing and just, all right. So, if you really want a local theory, in Einstein's sense, you're going to deny that the wave function is any kind of direct representative of anything physically real. Now you might say, oh, it's some kind of statistical object that really describes a collection of things. Or you might say it's some kind of subjective object that really describes a state of knowledge or something like that. All kinds of things you can do, but you're not going to take it as physically real. That, of course, just not to get too far into the problem of quantum mechanics, is automatically really problematic. Because then you say, well, how the hell do I understand two-slit interference? As Merman said at one, what is it? If the wave function is a representative of my knowledge, and the spreading of the wave function is a representative of my not knowing where things are, what, there's interference because my ignorance goes through both slits? That doesn't make any sense. Something physical, right, has to interact with both slits. All right. So I think any serious quantum theory, and I think the PBR theorem proves this, but I won't go into that, has to say there is a physically real entity that does more or less directly correspond to the wave function, and I call that physical entity the quantum state. So I'll try and use those carefully. Wave function for the mathematical object, quantum state for this proposed piece of ontology that it represents. Now, what about the elementary laws? As I said, Einstein's second characteristic, what he notices about field theory, is first of all, the ontology is local, because I characterize the global field by just characterizing its local values everywhere. But also, the laws, what I call the nomology, right? The account of the laws is local, because the laws are given by local differential equations in space and time. So I can check, right? If I want to know whether Maxwell's equations are globally satisfied, all I have to do is check in each little open region, each chart in an atlas, are they, is it satisfied there? Is it satisfied there? Is it satisfied there? And I can do that because they're local differential equations. And a theory with a local nomology, you can do that. If you have unmediated action at a distance, you can't do that, right? I mean, I'm watching a little particle. Suppose I've got Newtonian gravitational theory, and I think of it as having unmediated action at a distance. And I'm watching locally just a little test particle here, and it suddenly wiggles. And I say, gee, did that violate the laws of gravity? Well, I don't know. I have to check Was there some gravitational source 100 million miles away that wiggled? Right? And that wouldn't show up in an unmediated action at a distance theory. That wouldn't show up anywhere locally here. Good. So the nomology is just the fundamental laws. I'm now just repeating what I said. A theory with a completely local ontology can nonetheless be non-local if the laws postulate some unmediated action at a distance, right? So a local ontology is a necessary but not sufficient condition for what we would normally think of as a local theory. And this unmediated action at a distance, especially instantaneous action at a distance, is what Einstein referred to as spooky action at a distance, right? Spukhafte Fernwirkung. And as you'll see in the quote I'll give you, sometimes he calls this telepathy. Now, I'm going to probably repeat this 10 times, but this is, Bell's rhetoric, Bell works with a scalpel, right? And when he says something, he says it once and he says it right. And I work with a 2x4. I just whack people over the head. So I'm going to say a lot of things over and over again. What Einstein hated about quantum theory was not indeterminism. It was telepathy. It was action at a distance. Right? And everybody, when they say Einstein couldn't stand indeterminism, they're lying. And they're lying for a purpose, because they're misdirecting you about what Einstein was really worried about. Now, let me try and prove some of this. So here's a nice quote, which is, and I'll tell you a story about it. So here's the German, right? Here's the English translation. It seems difficult to sneak a peek at God's cards. This is my own translation. But that he plays dice and uses telepathic methods, as the present quantum theory expects isn't quite the right word, I don't know the right word. I cannot believe for a moment. Now, when I got interested in this quote, I wanted to track it down, and I went online. And I put in, God does not play dice. And I came up with this quote, but you know what I came up with? The quote online was, it seems difficult to sneak a peek at God's cards, but that he plays dice, ... I cannot believe for a minute. I'm not kidding. I mean, literally, what he was saying is ripped out, and 3 dots are put in its place. John Norton actually had it with the 3 dots in it. I wrote him an email. Right? Because the playing of dice and the use of telepathic methods are linked, as we'll see, to Einstein. In Einstein's mind, quite correct. All right. So, field theory. Classical field theory, classical GR are local, have a local ontology and also local dynamics. No problems. And as I said, the obvious way to specify local dynamics, if you've got a continuum and you've got an ontology that's sort of continuous, is by differential equations that are local in space and time. And then, as I said, you can check whether the laws are satisfied globally just by checking whether they're everywhere satisfied locally. And if you don't like unmediated gravitational forces, action at a distance, and one person who did not like that was Newton. Newton makes very clear that he didn't believe that gravity was unmediated action at distance. He says in a letter, no one in their right mind would think that. Right? Newton thought there were some particles, and if you pushed Newton, he would say, it's not instantaneous. I know if you push Newton, he'd say, of course, it's going to take some time if I wiggle the sun for the gravitational effects to get out to the Earth, right? Because whatever these particles are, they're going to have some transit time. But the way you get rid of, if you had unmediated action at distance, the way you get rid of it is by introducing a field. And then you wiggle the sun, and then that wiggles the gravitational field, and that eventually gets out to the Earth, and then the Earth wiggles, right? And then everything's nice and local again. So what's Einstein dealing with? He's starting with Maxwellian electrodynamics. He's starting with Newtonian gravitational theory, thought of as having a gravitational potential. He develops special relativity, develops general relativity. These are all theories that are local in their ontology and in their nomology. They are also happen both to be deterministic, right? In neither of those theories is there a fundamental chanciness. But as a matter of fact, that's incidental to the main point, because the main point is locality. And again, here's my whacking you again. It's the telepathy in Copenhagen that Einstein found unacceptable, not the indeterminism. The Einstein did not really care whether God plays dice, and this is made clear in a fairly famous, sorry, I really need that one, fairly famous letter from Pauli de Born. And you really understand the sentiment behind this. Also, Einstein gave me your manuscript to read. He was not at all annoyed with you, but only said you were a person who will not listen. This agrees with the impression I have formed myself, insofar as I was unable to recognize Einstein whenever you talked about it. It seemed to me that you directed some dummy Einstein for yourself, and then which you then knocked down with great pomp. In particular, Einstein does not consider the concept of determinism to be as fundamental as it is frequently held to be, as he told me emphatically many times, and he denied energetically that he ever put up a postulate such as, quote, the sequence of such conditions must also be objective and real, that is, automatic, machine-like, deterministic, right? Determinism wasn't the point. It was never the point. Locality was always the point. EPR. So, why so much talk about determinism? Well, there's a reason. There's the connection between determinism and locality runs through the EPR setup because it has perfect correlation. That is, if I do the EPR experiment and have my two analyzers aligned in the same direction, then I know for sure, probability 1, that the results will be opposite, and therefore by seeing the result up or down on one side, I know what the result on the other side will be. Okay? And in the EPR paper, when they give their criterion, again, it's not a definition. People don't understand the difference between a criterion and a definition. A criterion is just a sufficient condition. It's not a necessary and sufficient condition. They give their criterion of physical reality. They say, look, here's a criterion. If I can predict with certainty what the outcome of some experiment on a system will be without interfering with that system at all, then there must be some element of reality in that system, right? That's determining that outcome. And how could there not be? If there was nothing determining the outcome, how could I know for sure what it's going to be? But of course, I have to not interfere with the system in making my prediction. And the whole point in the EPR, what Einstein took for granted was locality. That is, by doing an experiment here, I do not interfere physically with a laboratory way the hell over there. And that's the point also of the photon in the box experiment. So Jos is exactly right. It was not trying to beat the uncertainty principle. Einstein's point was that I can determine, as I wish, the location or the energy of this photon that's way, 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 way far away by doing an experiment here. And his assumption was the experiment here can't have a physical effect on it. And so if I get a perfect signal, if I can tell from the outcome of this experiment what that is, then that has to already be a fact. The only other alternative is to say that my doing this experiment here brings it about that the photon has such and such a position, or brings it about that the photon has such and such an energy, and that would be telepathy. Right? So if you have these perfect correlations, and you want locality, then you're forced into indeterminism, into determinism, right? A local indeterministic theory cannot recover these perfect correlations. Because, Bell says this, but it's obvious, right? If I do an experiment here, and I get some outcome, And on the basis of that outcome, I predict that far away outcome. But that far away experiment is really indeterministic, and it could come out either way. Then there's no way my predictions can always be right. This is so elementary that Einstein figured everybody would see it, but it all gets lost, right? So the aim of Einstein, what he wanted to do was not recover determinism. He wanted to maintain locality. He looks at the EPR perfect correlations and he says, well, if you're going to have locality in a situation like this, you have to have determinism. You must have it, right? Any local theory is going to have to be deterministic. Here's Bell. He had a lot of trouble getting this across, and obviously 50 years later, we're still having trouble sometimes. It's important to note that to the limited degree that determinism plays a role in the EPR argument, and notice Bell again, to the limited degree, this was not Einstein's focus. To the limited degree that determinism plays a role in the EPR argument, it is not assumed but inferred. What is held sacred is the principle of local causality, or no action at a distance. Of course, mere correlation between distant events does not by itself imply action at a distance, but only correlation between the signals reaching the two places. These signals, in the idealized example of bone, must be sufficient to determine whether the particles go up or down, for any residual undeterminism could only spoil the perfect correlation. That statement says everything. Bell says it, he says, writes it once. If you read it, you understand. It is remarkably hard, this is still Bell, to get this point across, that determinism is not a presupposition of the analysis. There is a widespread and erroneous conviction that for Einstein, determinism was always the sacred principle. The quotability of his famous "God does not play dice" has not helped in this respect. So let's just to get entirely clear about this, you can have local indeterministic theories. Let's see what they're like. We proceed in two steps to get a local indeterministic theory. First, if no information or causal influence, whatever you want to call it, can go faster than light, then any common cause which produces a correlation, right? And this is, of course, you can get distant correlations through a common cause. That's the point of Bernoulli's socks, right? That's trivial. I cut a coin in half and send heads off that way and tails off that way. I get a correlation between those heads on one side, tails on the other. Nothing non-local going on. But what's important, the common cause has to, that produces the correlation must lie in the intersection of their past light codes, right? Because in a local theory, all the causes lie in the past light code. So if you have a common cause of two space-like separated events, and there's a correlation that's produced by a common cause, the common cause has to lie in the intersection of their back light codes. Therefore, if we condition on the content of the intersection of the back light codes, in a local theory, that's got to screen off the two events from one another, okay? So this is just Reichenbach's standard screening off condition. Any residual probabilities, now notice you could still have a probabilistic theory. The theory could still not be giving me deterministic predictions, but any residual probabilities for the two events should be statistically independent, uncorrelated. That is, seeing how this one comes out should not allow me to make better predictions about how the other one does, once I've conditioned on the intersection of the back light codes. The joint probabilities should just be the products of the individual probabilities in a local indeterministic theory. And I'll just note this because it also makes things easy. If you can come up with a local indeterministic theory, of course you can come up with some local deterministic theory that gives you all the same predictions. You just couple the thing deterministically to some white noise field that can be generated in some, however random way you like, but deterministically random way in the way we're talking about, right? Just use that to make the decisions rather than thinking they're fundamentally indeterministic. Obviously, any local indeterministic theory, you can get the same predictions out of a local deterministic theory. So you might as well, if you're worried about locality, just stick to deterministic theories. If you can't do it there, you can't do it. Now, what I did first was I conditioned on the entire intersection of the two backlight cones. We can now simplify that a little if we do one other thing, if we assume we've got a Markov process, okay? Which everybody basically does, and if you're not going to do this, you want to tell us up front, because it's a natural assumption. So if in addition to no spatial action at a distance, there's no temporal action at a distance, that is, if an event here is a cause or influences an event here, it's only because it has an influence on some continuous sequence of physical states that connect them in time, right? You can't have an event here just causing something here and jumping over the whole intermediate patch. And that's just the Markov condition. So then every causal influence from one event to a later one must be transmitted by a continuous chain of causation in time, and therefore that causal effect will register on every Cauchy surface. If you don't have that, then of course, the physics can be jumping over Cauchy surfaces, and the data on a Cauchy surface will not be enough to determine things and blah, blah, blah. But nobody ever expects this kind of temporal, nobody's using theories with this kind of temporal action. So if we assume now, in addition to no spatial action at a distance, no temporal action at a distance, then it's sufficient. I don't have to condition on the entire intersection of the backlight cones. It's sufficient to condition on a partial Cauchy surface that cuts across the intersection of the backlight cones. A Cauchy surface or a thin sandwich, depending on exactly what you're doing. If it has to be a sandwich, it can be as thin as you like. And this is a diagram that comes up that Bell uses in Undeveloped Routine, which is one of the later things, almost about the last thing he published. It was so late that if you're a real old geezer like me, I had the original version of Speakable and Unspeakable, and it didn't have this paper in it. And it shows up only in like the second edition, so I wasn't that familiar with it. But I was just rereading it, coming here on the plane. Man, Bell, I mean, you can't beat Bell. It's funny, it's on target. And he says, look, I've got region A, I've got region B, the lambda and the C are jointly complete description of the physics of the situation in this sandwich. And you can see it's important that it actually cut above where the two backlight cones diverge. And that allows him to do his analysis on that basis. And you say, in a local theory, right, once I condition on lambda and C, then even if it's a probabilistic theory and there are probabilities for A and B, they'll become statistically independent. Okay, so that's the assumption of Bell-locality. That's the way he characterizes the locality assumption in Undeveloped Routine. That's the condition that he uses to prove his theorem. And if the theorem followed from that condition alone, and the theorem says, no theory that is local in the sense I have just defined can violate this inequality, and the equality is violated in nature, then you conclude nature's not local. Okay? Period, end of story. And I have to say, when I do a kind of everyday presentation of Bell's theorem, that's the way I present it. I say Bell made a locality assumption, he derived a consequence from it, the consequence turns out to be falsified, the locality condition is therefore falsified, nothing to do with quantum mechanics. There's not a word about quantum mechanics in Bell's proof, right? It's not about quantum mechanics, it's not about hidden variables theories, whatever the hell that means. It's about any theory, any local theory. Local theories that are built on mathematics that haven't been invented and won't be invented for 150 years. Doesn't matter. That's the beauty of the theorem. It's not a parochial theorem. Is that really the only assumption that goes into the theorem? Well, no, it isn't. That's what this talk is about. I say, I've certainly said things like that's all that goes into it. I lied, but it was a noble lie. It was not to what I would think to be mislead the audience that I'm talking to. So let's talk about the other assumptions that have to go into. Sorry. go into it. There are some other tacit conditions that have to be satisfied if you want to say, we know that the world is non-local, experimentally. Trivial. It better be that the experimentalists aren't just making stuff up. Okay? I mean, if you want to say, can you explain this data with a local theory? I say, yeah, the experimentals have been bought off by the Bell Foundation, right? And they're just on the payroll, and none of this stuff ever happened. Okay? Yeah, well, then physics could still be local. But what's weird about that, right? What's weird about that is that if you don't make basic assumptions about the reliability of your experimenters, yes, you can get out of this conclusion, but all of empirical science gets thrown out the window as well, right? There's just, what you can't do in an intellectually respectable way is raise doubts like this in one circumstance and say, I don't like Bell's result, so I'm going to be really, really picky and say, oh, it could be this, it could be this. But then in the next thing, you get a theory you like, and all those doubts go out the window, right? If you're going to raise that kind of global skepticism, you're done with science. So this is what I called in the abstract a kind of transcendental argument in Kant's sense. There are conditions that have to be satisfied to do empirical science. They're not guaranteed by logic, right? Logic doesn't guarantee that experimentalists don't lie. But just understand that if you don't like this result, and you're going to say, well, I think the experimentalists are lying, and I'm just going to say, and you say, well, the inspector checked, and well, I think the inspector's lying. You actually see this in the Trump administration, right? Anybody who says something they don't like, it's fake news. And if they hire an inspector to check whether it's fake news, and they say it's not fake news, then they say it's a fake inspector. Okay? And logic can't stop you. Right? This was a point Klein made a long time ago. If you want to hold on to a belief in the face of all empirical evidence, you can always do it by making radical enough adjustments in the rest of your world picture. Yes, logic will not force you, but this is the kind of assumption that if you're going to say, this is what I'm questioning, then just hang up your hat and say, I'm not doing empirical science anymore. Some other assumptions. Let's suppose the experimenters aren't corrupt. They're sterling characters. They would never lie. There are other assumptions we make. We assume that the experimenters and us are not somehow plugged into computers by wicked aliens like in the Matrix, generating a virtual reality that's governed by whatever virtual physics they want to make up, whereas their computers are run by good old Newtonian classical mechanics. Okay? Okay, could be. I can't prove that's not going on right now. But again, if that's the kind of doubt you want to raise, look, we do Descartes' meditation. We deal with this kind of stuff all the time in philosophy. And you just want to say, okay, now be serious. We assume that the labs actually were at space-like separation, right? Because you get this data, it's only important. The data doesn't mean anything if the experiments were not done in space-like separation. If one experiment was done and then the next experiment was done the next day, of course there are ways to arrange whatever correlations you like, okay? We assume that when you do an experiment, and it seems like odd to say this is an assumption, that there is a unique outcome. Right? I did a spin experiment, I either got up or down. Now a many worlds guy is going to come along and say, no. That didn't happen. You did an experiment and you split, and one of you saw up and the other of you saw down, and Alice split and one of her saw up and the other saw down, and when the two Alices came to talk to the two Alices, each Alice, to the two Bobs, each Alice could only see one Bob, and each Bob could only see one Alice, and they report, all this kind of stuff. Okay, right. Many worlds you have to deal with separately. I would have a lot to say about it, but I don't want to bore you with that. I know that there is not a many worlds guy, so that's not relevant here. That's a discussion you would have to have. Okay. So what's the logic of the argument? So as Bell notes, the logic of the argument in its simplest cases, and the simplest cases is where there are these perfect correlations. You don't need them. CHSH doesn't need perfect correlations, but where you have them, you have this logic of the argument is the perfect correlations require determinism in a local theory. Let's look at local deterministic theories and then prove they can't violate the inequality. Okay, so the logic is, from the perfect correlations, you first infer that the results on each side must be predetermined. There can, in fact, be no fundamental dice playing. And starting from this conclusion, which is the conclusion of the PR argument, and if you read Bell's original paper, he says this in about the first paragraph. He just assumes the reader's going to understand it. Then you can ask, well, gee, if in a local theory you have to predetermine all the outcomes, can they in fact be so predetermined? So that no matter which experiments are done in the two labs, the outcomes will be consistent with quantum mechanics. Now, at this point, Bell gives his theorem, and it's very beautiful, but it is, as we know, a statistical theorem. It has to do with probabilities and long-run frequencies. And as far as the logic goes, it's much nicer and more beautiful to look at the GHC example, because as Merman noted, I mean, David Merman always, he said early on, he thought something, this intrusion of probabilities and statistics into Bell's theorem might be very deep. It might be telling you there's something about this that fundamentally has to do with probabilities. But when he saw GHC and it's all ones and zeros, he said, nope, I was wrong. Right? So GHC is much nicer. It's much prettier, and that's the one I always use. And in GHC, you have the same perfect correlations in the sense that I do 3 experiments. If you don't know, I'll show you a picture in a minute. You do 3 experiments, and from the outcomes of any 2, you can predict with certainty the outcome of the third. Okay, so it's like in EPR, from this one I can predict with certainty the outcome of that one. Here, from any pair, I can predict with certainty the outcome of the last. So let's look at it. So the setup is like this. We have some source that's producing the appropriately entangled triple of particles. They go off to some Stern-Gerlach apparatuses. And the choice is that each Stern-Gerlach apparatus is either oriented in the X direction or in the Z direction. That is the choice that can be made by the experimentalist or in the experimental labs freely, which is what we're now going to talk about. And then you get these predictions, which is that if you started in this GHC state, if we measure all 3 in the X direction, we always get an odd number of up outcomes. It might be 1, it might be 3. That's not predicted but with certainty, but it is predicted with certainty that it'll be an odd number. If instead we measure 2 in the Z direction and the third one in the X direction, then we always get an even number of up outcomes, either 0 or 2. And those are predictions with certainty. And then you have this argument. This is the way Merman presented it. It's very beautiful. You have measurement of X on particle 1, X on particle 2, X on particle 3. The 4 lines represent 4 different global experimental arrangements that we care about. The dotted line is the experimental arrangement where we measure X on all 3, and we're going to get an odd number of ups. And the solid lines are where we measure 2 Z's and an X, and we're going to get an even number of ups. And the question now is, in a local theory, I would have to predetermine the outcomes of all these experiments, put a U or a D in each circle. Can I do that in a way that satisfies these constraints? And the answer is no. And if you don't believe it, I mean, you can try yourself, but the nice argument that Merman gives is, suppose you could do it, suppose you could write U's and D's in these circles to satisfy these constraints. Okay, come down the dotted line, pick up the tokens, throw them in a hat. You just pick up an odd number of U's. Now come down this line, this solid line, you've just picked up an even number of U's. Throw them in a hat. The next solid line, even number, throw them in a hat. The last solid line, even number, throw it in a hat. Even, odd. You now have an odd number of U's in the hat, but you picked up every one twice, right? Because every circle is at the intersection of 2 lines. There is no conceivable way you can stick U's into those circles that will satisfy that. That is a mathematical theorem, period, end of story. No local theory can possibly reproduce this. Now, there is another assumption. And this is what this is all about for people who want to try and save locality. There is a statistical independence assumption. that Bell uses, and he's aware that he uses, and he defends using it. Okay? We know, and I just proved, that no local physics can predetermine the outcomes of these 6 possible experiments in such a way that they will always satisfy the predictions of quantum theory. Okay? For all 4 of the possible experiments that could come up. So, if I had a local theory and I predetermined these things somehow, there would be, if I randomly were choosing between these 4 possible experimental arrangements, about 1 in 4 times I'd get it wrong. Right? I'd get a bad result. I'd get a result in conflict with quantum mechanical predictions. So now we make the final mathematical assumption of statistical independence. It is the assumption that the sampling we're doing from these, if I do this experiment over and over and over again, right, I get a triple of particles, another triple of particles, another triple of particles, that the sampling of those particles is random in the sense that the statistical characteristics, the physical statistical characteristics of the subensembles that are sampled with one experimental arrangement are the same as the statistical characteristics of every other subensemble, because they're all drawn from the same big group by random sampling. That is, I treat the experiment, these choice of experimental conditions as random sampling in the proper mathematical sense of random. So if you assume that, then you say after a long course of experiments of local physics, you can calculate the probabilities, right? It becomes arbitrarily close to 0 that they'd always come out right, because you just have to be very, very lucky. You would expect in a long course of experiments, in a local theory, you'd get the wrong outcomes at least 1 time in 4. Now, what about this assumption of statistical independence, this random sampling assumption? It has this same kind of transcendental character. This is what I want to say. That is, it's not, logic doesn't prove it, right? It's not a theorem of logic, it's not a theorem of mathematics. But if you don't make that kind of assumption, you can't do empirical science anymore. For example, we have observed a strong, robust correlation between mice being exposed to cigarette smoke and mice developing cancer in controlled experiments. What does that observed correlation mean? In randomized controlled experiments. That means nothing about the causal efficaciousness of cigarette smoke in causing cancer if the mice who are already predisposed to get cancer always somehow or other end up in the experimental rather than the control group. And the smoke has nothing to do with it. Okay, that's logically possible. It's just insane to believe that, right? We would regard that hypothesis, it would make the cigarette manufacturers very happy, and we would regard it correctly as an insane hypothesis. You say, wait a minute, whenever I take a group of mice, and by any method I can think of, I flip a coin, I run a random number generator, I check the number of shares of stock that have just been sold on the Dow, by any method I can think of, I sort them into an experimental and a control group. Somehow or other, all the mice who are about to get cancer go into the experimental group, and all the mice who are genetically predisposed never to get cancer go into the control group, right? No matter how I do it, you would just think that's crazy. And whether you think it's crazy or not, if you don't make that assumption, again, all of empirical science is wrong, right? What we think of as the gold standard of tests of causal claims, which are randomized controlled trials, wrong. Okay, here's now the last thing I'm going to say, the last word. Many words will go to Bell. Bell. He deserves it, and he said it all right. And this is from Free Variables and Local Causality, which is a paper that has not been read with enough care. I'm just going to read a long quote from him and just take it in, and then I'll. So Bell says, suppose that the instruments are set at the whim, not of experimental physicists, but of mechanical random number generators. And by the way, anybody who thinks this has anything to do with free will, no. Mechanical random number generators do not have free will. Nobody thinks they do. Okay? Nobody ever thought they did. But as Bell says, they serve his purpose actually better than the whim of experimenters. Suppose that the instruments are set at the whim, not of experimental physicists, but of mechanical random number generators. Indeed, it seems less impractical to envisage experiments of this kind with space-like separation between the outputs of two such devices. Right? Random number generator here, random number generating their numbers really quickly, which they have to do if you're going to do these choices in space-like separation. Then to hope to realize such a situation with human operators. Could the outputs of such mechanical devices reasonably be regarded as sufficiently free for the purposes at hand? That's a technical phrase that he's introduced earlier. Sufficiently free for the purposes at hand. I think so. Why? Consider the extreme case of a, quote, random generator, which is in fact perfectly deterministic in nature, and, for simplicity, perfectly isolated. In such a device, the complete final state perfectly determines the complete initial state. Nothing is forgotten. And yet, for many purposes, such a device is precisely a forgetting machine. A particular output is the result of combining so many factors of such lengthy and complicated dynamical chain that it is quite extraordinarily sensitive to minute variations of any one of the many initial conditions. It is the familiar paradox of classical statistical mechanics that such exquisite sensitivity to initial conditions is practically equivalent to complete forgetfulness of them. To illustrate the point, suppose that the choice between two possible outputs corresponding to A and A prime, right, I'm going to set my Stern-Lerach device either at X or Z, depended on the oddness or evenness of the digit in the millionth place of some input variable. The fixing of A or A prime indeed fixes something about the input, i.e. whether the millionth digit is even or odd. But this particular piece of information is unlikely to be the vital piece for any distinctively different purpose, i.e. it is otherwise rather useless. With a physical shuffling machine, if we were throwing dice or doing, lotto balls or something, we are unable to perform the analysis to the point of saying just what peculiar feature of the input is remembered in the output, but we can quite reasonably assume that it is not relevant for any other purposes. In this sense, the output of such a device is indeed a sufficiently free variable for the purpose at hand. For this purpose, the assumption, one, that is, the assumption of statistical independence, is then true enough, and the theorem follows. And I think that is the last word on the subject. So I will end there.
Over time, but always time for questions.
That was a very long story. As you know, long stories are much easier to gain error of thought than short stories. This is not mathematical tool, it's a story. Now, my point, can you show the diagram where you have this space-like diagram with the electrons and the A and B?
Yeah. The one from La Nouvelle Cuisine.
Yes, exactly.
Now,
There's one basic assumption made there which is not evident at all. And that is that if you keep lambda, C, and C the same in the repeat experiment, that then you can choose little a and little b different.
no, he does not make that.
All,
He did not make that assumption.
I'm talking about the settings chosen.
He does not make that assumption. He assumes that those settings are themselves functions of lambda and C.
Yeah, but those settings, the theorem is about when you change those settings and you keep the statistics lambda and C the same.
No,
Then,
that's not correct.
no, but
The assumption is if there were different settings at A and B, lambda and little c would somehow have to have been different, because this is a deterministic theory.
yeah,
But the
in
point
this
is,
theory,
he's saying if you're using a physical randomizing device,
yes.
that difference will not make a difference for any other distinctively interesting purpose.
So, very good. Take that mechanical random number generator.
Mhm.
Now, Now suppose that on these curly lines, the Cauchy data of the whole system are exactly identical. Then this random number generator, whether you like it or not, must give the same answer.
Sure.
So you can't change the random number generator without making some changes in the past.
Sure.
So
He doesn't deny that.
But that includes that photon that you're looking at.
Yes.
And that is the whole point why you can get around that theorem.
No, he doesn't deny anything you just said. You haven't understood his point.
That theorem.
You haven't understood his point. His point is, if you make the changes, if you imagine changing, I have a generator that's generating the digits of pi, and making the decision on the parity, can I finish? Is making a decision on the parity of the digits of pi. And now you say, well, what if it'd been E instead of pi? Well, for it to be E, there now have to be you have to put a different computer in, and you have to reprogram it, and blah, 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 and that'll show up in lambda and C. But can I finish, please? Can I finish? His point is that those differences will not reasonably be thought to make a difference to the state of the incoming particles.
Why? Of course it does.
Statistically, because it's the same statistical assumption you make when you do any analysis in statistical mechanics.
I know that, but still, there's no reason why that photon should be considered independent of whatever else happens in that world. So, on the wavy lines, there are the Cauchy data of the entire system.
Yes?
If you choose those identical, there will be no way in which your random number generator could be set to do something else.
Yeah. Again, all I can do is repeat. He doesn't deny anything you're saying. He understands all
It
that.
doesn't fall.
It doesn't follow logically. It follows from a principle of physical analysis that we need to do physics. It follows in the same way when Maxwell proved the Maxwell-Boltzmann distribution, he made a statistical independence assumption, and it was the correct physical assumption to make.
So I agree with that, but that is the standard way we always do physics. You can say we always do science that way, but that's precisely what the hidden value theory that I would propose denies. You should not do physics and science this way. You should say, well, if the only hidden value theory that possibly works is one that works exactly for the entire universe without any error being made anywhere. So you have to have these, if you choose all your data identical, there's no way you can change the setting of A or B or the random number generator or anything. They'll also be fixed. As soon as you touch the random number generator, that touch must have an effect in the past as well.
Yes.
You agree so far. So you
Yes.
can't make a change in the random number generator
Yes.
without changing the past.
Yes.
That change in the past will, whether you like it or not, also affect the wave function of that phone.
It will have some effect. That it would have the kind of effect you would need for the sampling not to be statistically random
Yes.
is what Bell would say incredible, and he's quite right.
It's incredible, but there's no reason, but you can't prove it.
No, but it's incredible, so I shouldn't
Incredible,
believe
but not disproven.
It's incredible to me that the experimentalists are all lying, but I can't prove they're not.
No. But you can't disprove.
I can't prove the experimentalists aren't lying. How can I prove it?
The mechanism that I've involved to exactly get around this problem, because I do agree this is an important question. I really think it's an important point. The mechanism is precisely this ontological basis. If you only look at ontological states, there can be no violation of Bell theorem.
But there are violations of Bell's theorem.
Yes. So, but the whole thing is if you have you have no quantum mechanical effects. You can't measure non-commuting operators if you have only ontological states. So, the setup, the whole experiment cannot be done in narrow theory if you assume that those photons will be superpositions. So any experiment you do requires you to introduce operators at A and B, which are non-commuting. The whole thing of quantum mechanics is that things are not commuting. But if everything would commute, you would never have a violation of Bell's inequalities.
So can I just, there's a mismatch of level of terminology. in order to do the experiments, I don't have to introduce any operators. In order to do the experiments, I need 3 Stern-Gerlach apparatuses. I need a source that's been built by some specifications, and I need to watch and count and see what comes out. Now, whether a theory to account for that needs something that commutes or doesn't commute or whatever is neither here nor there from the point of view of the logic of the argument.
Quantum theory says that if these operators are non-commuting, then you get a violation of Bell's theorem. And Bell says, experimental physicists do this all the time, they produce these observables, I have no problem with that, and therefore there's a contradiction. But in an ontological theory, the observables you eventually look at are all commuting. And you can't do an experiment where things are not commuting. So that means that whatever is happening must be of the kind I've told you, that this photon cannot be independently in a superimposed state.
I'm really, you don't disagree with the mathematical statement that you cannot predetermine in that little graph. I can't put U's and D's in the circles so that it will satisfy those constraints.
But the whole point is that to set this thing up, you need to work with non-commuting operators. Because you have a theory that tells you what comes out. And that theory is quantum mechanics. And that theory uses non-commuting guys.
Suppose quantum mechanics had never been invented, but some experimentalist in a lab fooling around just developed Stern-Gerlach magnets and noticed that things either dotted here or dotted there, and they just went and did 3 of them, and they started collecting data, and they didn't have a theory that predicted anything. But they noticed after a while that the data come out as in fact quantum mechanics predicts. And they thought, gee, how can we explain that? And now they get Bell's argument that says you can't have a local physics that will explain it.
The whole thing is you are using, whether you like it or not, you're using a model that describes those photons when they were produced in a spin-zero mind state. Well, the usual blah blah of quantum mechanics, at point C, you generate this entangled pair of photons. Only if you know that those photons are entangled, you get the contradiction with Bell's theorem. If those photons were not entangled, you wouldn't have a contradiction.
The contradiction is just in the data.
Yeah.
It's just in what the world does. The world contradicts.
No, but you are assuming that the photon stays identical. If you do repeat the experiment again.
I'm not making any assumptions about repeating experiments. I know you can't repeat experiments. You do sequences of experiments. The assumption is that you're randomly sampling. The collection, if you agree that in a single run, in a local theory, you could not predetermine the right outcomes for all possible experimental settings, then you agree that in every run, there is at least one experimental setting that would have gone bad. And then you assume that you're randomly sampling, so that if I do this 1,000,000 times, I would hit the bad one somewhere.
You agree that if you assume that those lambdas would actually depend on the little a and little b, then the whole problem disappears.
No, because they do depend on it. Bell knows they depend on it. It's how they depend on it.
The lambda in there depends on both little a and little b.
But
If that stays, then you have no problem.
well, the dependence goes the other way. Little a and little b, and capital A and capital B are going to be functions of C and lambda.
The contradiction comes if you have a given lambda, and then you can, once you got lambda given, you can change the little a and little b.
That's not the
Then you get the contradiction.
No, that's not the assumption. The assumption is your random, is your statistically random sampling from a set of operators. That's the assumption. That's the mathematical assumption that goes into the
Bring
thing.
up this random number generator? Why did you bring up this random number generator?
To show how reasonable that assumption is.
You would choose a little a, little b, but if you experiment once, you will change contradiction.
But In the GHZ thing, in a local theory, there's a 1 in 4 chance you'll see a mistake even if you only do it once.
So,
And if you do it a million times and there's a 1 in 4 chance every time you do it, it's, you know, it's not guaranteed by logic, but of course you think you would miss about 25% of the times in the language.
Shall we continue this later and give a few other questionnaires the opportunity to ask a different question? We don't.
Thanks, Tim. That was a lovely talk. Let me have one go and try and make pizza. If we disallow the statistical dependence loophole, then the world is non-local.
Yep.
Now, Einstein wouldn't outright that.
Correct.
And Einstein had a transcendental argument that if you allow non-locality, then you can't do science.
Right.
Now, how do we fix that tension?
Yeah.
It's because in quantum mechanics, non-locality is constrained by the no-signaling theorem.
Mm-hmm.
Without having had good discussions about what's happening and so on and so forth, it might have initially seemed implausible that one could have non-locality that still allowed you to do science.
Mm-hmm.
But now we've got a grip on that.
Mm-hmm.
I think we need to give the statistical dependence loophole a fair chance and see. Of course, statistical dependence of a wild sort is going to make all of science impossible. But if a theory can in fact be developed where that statistical dependence is there, but is constrained in the right way, then we can all be happy.
Yeah, look, and of course, I agree with that, and Bell himself agrees with that. Einstein, I would not say Einstein had an argument that radical non-locality would make science impossible. He asserted it, but he didn't back up the assertion with any detailed reasoning, right? And of course, one looks at it and say, well, I guess quantum mechanics is a counterexample of that because it's a non-local theory, but we can do science. Okay, so then you sort of you stop and think, as you did. You say, well, what did Einstein had in mind? Well, he was thinking, gee, if every little particle in the universe could make a difference to whether this comes out up or down, then how could you ever get enough isolation to deal with quasi-isolated systems and blah blah blah? And now you can go into quantum mechanics and sort of answer those questions. And as you say, no signaling is part of it, right? And on why you get good statistical. But of course, we already know that when you do statistical mechanics, there's a way in which this tremendous sensitivity, and that's just what Bell says when he talks about in classical statistical mechanics, this tremendous sensitivity to initial conditions is the same as forgetfulness of them, right? Because you can then give statistical arguments and typicality arguments that say even though individual outcomes depend quite sensitively on a wide array of things which you'll never know, you can nonetheless say that you'll get typical statistical outcomes if you do large sampling, right? So you do, and Bell says something like, look, people could try to come up with theories that deny statistical independence. I myself will not try to create such a theory, but I'll listen if somebody has one. And he's a polite guy, more polite than I am. And it's the right thing to say, of course. But you do have to make. We have in hand several different explicitly non-local theories that are formulated with the kind of mathematical and conceptual precision that Bell wanted. I mean, maybe not quantum field theory, but anyway, Bohmian mechanics, GRW theory. These don't have a measurement problem. They're mathematically well defined. They work. They make all the right predictions, and they're non-local. And you do have to make a judgment. If someone says, well, maybe, maybe you could eventually develop a theory that somehow denies statistical independence. And I mean, you do have to make a judgment about whether you want to deflect your attention to that rather than working on trying to make the things we have to hand that work in the non-relativistic context, for example, work in a relativistic context to bring gravity in. There's a lot of work to be done on those things.
Did you now accept the peace offering or not?
I don't know. It depends on who made peace with by whom.
Well, we're 20 minutes over time, but the lady in the back there, can you throw catch?
Thank you for the talk and the microphone. Well, as far as I remember, I think
Closer.
Closer. There? I think it's not working anyway.
It's not working.
Yeah. So as far as I remember, the GHC Set example proves it's more like a Cohen-Specker type of theorem than a Bell type of theorem.
No.
Does that know that you can't hear me, or is that know that it's...
No, that's not true. It's a Bell theorem.
In the sense that it proves that you cannot assign all the variables to all the system. And so it's contextuality, that variables are contextual.
No, that's not. No, it's a non-locality theorem because you can put the three labs in space
Yeah,
on
and
separation.
I think that non-locality, it's a locality theorem out of the non-contextuality.
Yeah, look,
It's
if you
a
take...
consequence that you cannot assign simultaneously variables to all the systems.
If you take a look, Cauchy-Specker is not a non-locality theorem. If you can take a contextuality theorem, a theorem that says you need contextuality, and then implement it in a setting where the context relevant to the outcome of this experiment is the setting of the apparatus on that experiment, then you've got a non-locality theorem. And that's what you do in GHC. That's why you separate these three labs. You put them in space-like separation. So it's a Bell theorem.
But I think you only get that out of counterfactual reasoning. So,
No.
Okay.
That's nothing about counterfactuals.
Okay.
I mean, look, how could there be anything about counterfactuals? I just put up a diagram and said you cannot fill out this diagram with U's and D's so that for any of these four experiments,
There's the
you'll get the
counterfactual-
right thing. Can I finish?
Yeah.
Therefore, if it's a local theory and I've just sent out 3 particles, at least one of those 4 experimental settings will give the wrong result. And if I do this many times and I never get the wrong result and I'm randomly sampling, then you say that can't be right because I would get the wrong result. There's nothing about counterfactuals in that. I didn't use a counterfactual anywhere.
Comparing the 4 experiments.
What? Sorry?
Comparing the 4 experiments, the 4 different
I'm not
settings.
comparing them. I'm randomly sampling. If I say I'm randomly sampling from a set, that's not a statement about counterfactuals.
Okay.
It just isn't.
Okay.
Sorry, the counterfactual thing was that you opened those boxes.
That I opened.
Well, you had, in GHC case, you had the, binary numbers which are all adding up to 10. So you can't get those.
But that's just the predictions, that you always will either get in one setting, you always get an odd number of results, in the other setting, you always get an
thing you
even.
did was you looked at those numbers to see whether they're even or odd.
Well, I looked at numbers. I was just trying to see mathematically, can I pre-assign these results that satisfy these conditions? And the answer is you can't. That's just math.
Mathematical proof required to open. That's the
Well, I don't mean, I didn't open anything. It's just a mathematical question. Can I put U's and D's in a bunch of circles that satisfy us? There's nothing about opening boxes.
But you assume that the content of that circle is the same whether you consider it in the context of this experiment.
Yes, that's the locality assumption. That the outcome in this lab does not depend on what experiment happens to be done in the other labs. That is the locality.
Even if it's controversial.
Again, I don't understand what, people think, this is just infected the Bell literature forever. People say, oh, there's an assumption of counterfactual definite. It's like saying there's an assumption of determinism. And as Bell said over and over again, determinism is not an assumption, it is derived. If you have a deterministic theory, of course, that theory will make counterfactual assertions, right? In a deterministic theory, if I then say, oh, what if it had been different in such and such a way, and I'm precise enough about how it would be different, the theory will tell me what would have happened. But that's not an assumption, that's something that's derived from the locality assumption via deriving determinism, as Bell said. And as Bell said, it's very hard to get this point across, which it seems to be.
Well, I think we should end here. It was difficult to get the point across. Let's